Oh, are you finished? Okay. Well, thank you very much. Hope everybody can hear me. Hmm? Okay. So I thought that this lecture could be used as an illustration of some specific examples of much of the theory that we discussed in the morning. So let me begin with some generalities, which, since I know that some of you are working on uniform distribution of sequences and things like that, so let me begin with something that's probably familiar to you. So recall Weyl's criterion for uniform distribution mod 1. So given a sequence of numbers, given a sequence of real numbers, x sub n with 0 less than x sub n less than 1, maybe we don't use 1 maybe, but then the sequence x sub n is said to be uniformly distributed if and only if these exponential sums are all small equal 0 for all m not equal to 0, m an integer. So for all the integers m, we have to check these exponential sums. And of course, you probably only need to check positive. And just simply by complex conjugation, you have the same result. But anyway, this is the Weyl criterion that is familiar to probably most of you. The interesting thing is that what is lurking behind this Weyl criterion is group theory. So there's a group here, and then what are these e to the 2 pi I m xn's? Well, they're characters of the group. So the group, the underlying group in Weyl's criterion is the torus, R mod z is the torus. And the irreducible characters of this group of T, let's call this T, of T are chi sub m of theta e to the 2 pi I m theta. So these are your irreducible characters. And so one could interpret perhaps the Weyl criterion in a larger context. So there's a generalized Weyl criterion. Which says basically let G be a compact group. Then a sequence x sub n of elements capital X. So capital X is the set of conjugacy classes of G. So basically, G is a compact group. It has a certain power measure on it, and we can restrict our attention to the space of conjugacy classes, and the Haar measure descends to a Haar measure on X. And the question of how the elements of how these elements are distributed in this topological space is then reduced to an evaluation in terms of characters. If I write below this line, is it okay or is that bad? It's okay. Okay. So now, so the sequence is uniformly distributed if and only if summation chi of xn, n going from 1 to capital N, 1 over n, tends to 0 as capital N tends to infinity. And this we want, of course, for all characters chi, which are not the trivial character. As long as it's not the trivial character, of course, the trivial character is just 1, of course. But for all the non-trivial characters, we have to have this. So this is really the generalization of that case because of applied to the torus. Now, this you may know about this thing because much of the beautiful theory, what's called Petter-Weil theory, arose in this context. Now, in the context of L functions, as we were discussing at lunch, the applications of some of the exotic L functions that we spoke about earlier in the morning is still to be, determined. Many classical examples exist, but clearly the universe of the Langlands automorphic L functions is much larger than the classical prime number theorems. So the Sato-Tate conjecture is going to be a case in point. And this presentation that I'm going to give right now is really due to Sayre. You can find it in his book, Abelian elliptic curves and Abelian elliptic representations. You can find it there. So the idea, a general formalism due to Sayre, is the following. Suppose we have for each prime p, I'm still going to use the group G as a compact group. For each prime p, a map xp. And in X. So G is as before. G. So I should have said maybe let G be a compact group. X, the space of conjugacy classes. Suppose we have for each prime P a map equals to XP in this space. Then the XPs are equidistributed if and only if the L function the L function, which I will describe in a second, for all rho irreducible representations of G, they don't vanish on the line real S equals 1. And so here, the L function is LS rho, defined in the Artin style, product P, determinant 1 minus rho XP, P to the minus S inverse. So for each representation rho of the group, given this data of the XPs, I will concoct this L function, and I will say that firstly, we have to, before we talk about real S equals 1, we have to talk about analytic continuation here. The point is that these L functions, because the representations are, the eigenvalues are all shown to be at most absolute value 1, this converges absolutely for real S bigger than 1. And so one needs analytic continuation of LS rho to real S greater than or equal to 1, and non-vanishing on real S equals 1. And then once we have these two pieces of information, we apply the Tauberian theorem as I discussed in the morning, and then deduce that equidistribution property. That means what you will find is in the context. I know that I discussed the equidistribution theorem with the residue R, but if it's holomorphic and not there is no pole, then the residue is 0. So the limit that you're looking for emerges from that Tauberian theorem. So for all the non-trivial irreducible characters, you get exactly what you want, provided you have analytic continuation to the line real S bigger than or equal to 1 and non-vanishing. So this formalism of Sayre is very pretty because it reduces all questions of uniform distribution in general groups to a kind of L function setting. So the question then is this concocted L function a meaningful object, or is it something that arises naturally in this context? And it turns out in cases of interest, like the case I'm going to illustrate, these things arise naturally from the Langlands program. So, okay. Now, what is the Sato-Tate conjecture? The Sato-Tate conjecture involves an elliptic curve. So let E be an elliptic curve. And for that, you can just take y squared equals x cubed plus ax plus b with a and b integers, if you like. That's an elliptic curve. And you can reduce the elliptic curve modulo p and count the number of solutions. And if you look at this set and try to calculate, technically what we really should do is we should throw in a point at infinity. So don't worry about that. That's just a minor convention. So when I throw that point in, I include this one. That's all. But this is not terribly important. So there's a formula for the number of points on the elliptic curve given by p plus 1 minus a sub p, where a sub p is bounded by 2 square root p. This is called Haas's inequality. We know this, I think this was first conjectured by Emil Artin in his PhD thesis, and Haas proved it in the 1930s. Okay, so we have this estimate. Now, this is where the Sato-Tate conjecture begins. This is reminiscent of, if you remember, Ramanujan in the morning talk discussed the tau function, and in that context, he conjectured the tau of p is less than 2 p to the 11 halves. So there it's a higher weight. Here we have a weight 2 modular form in the background. That was a weight 12. So that's this reason for the discrepancy. But the two conjectures are similar in nature. Yeah. Now, so in other words, i.e., a sub p divided by 2 square root p is always between -1 and 1. The question is, how are these numbers distributed in this interval? How are these numbers distributed in -1, 1 as the prime varies? So the Hasse estimate tells you always this holds, but is AP always clumped very close to 2 root p, or is it -2 root p, or is there some sort of regularity? So how are these numbers distributed? So here's this very concrete question about elliptic curves, about these numbers, and the only way to answer it is through the Langlands program. Let's explain that now. And this, of course, this formalism is pretty general, but to get your hands on these functions in a specific case requires you to handle the automorphic L function. Now, it turns out that there are two cases to consider in the context of elliptic curves. Elliptic curves kind of come with two varieties. One's called with complex multiplication, others without complex multiplication. So if we look at the endomorphism ring of an elliptic curve, it can either be of two types. It can either be ordinary integers, or it could be some sort of order in an imaginary quadratic field. So this is not hard to prove. I'm not going to do it now, but so these are the two cases. The endomorphism ring either is ordinary integers or is larger, and is an order in this thing. In this case, we say the elliptic curve has no CM. Here we say the elliptic curve has CM. So CM stands for complex multiplication. In other words, there are extra endomorphisms coming from imaginary quadratic fields. Now, the question of equidistribution that is being asked there is different for these two cases. So if E has CM, the answer is easy. I put that in quotation marks with retrospect. And in some sense goes back to Hecke. And if E has no CM, very difficult. And it goes beyond the modularity conjecture that Wiles used to prove Fermat's theorem. It goes beyond that. So it's harder. Very difficult. Needs potential automorphic. Okay, so I put these words in quotation marks just because the experts will know what that means, and the non-experts will not understand even if I explain it. So let's leave it like that for the time being. So unless I have to use this, which I will at some point. Now, coming back to this question of equidistribution, the issue turns out to be is it possible to rephrase this question in Sayre's formalism? And this is the novelty, I think, of that book, those lectures that Sayre gave at McGill um, on elliptic curves and abelian analytic representations. He emphasized in that book that the right group to use is the special unitary group. And the conjugacy classes are parametrized by x theta e to the I theta 0, 0 to the minus I theta. In other words, Jordan canonical form or whatever, the eigenvalues are of this type, so you can parametrize all the conjugacy classes by the unit interval 0, 2 pi 1, 0. And what we do is we take AP over 2 root P, and we write it as cosine of theta P for some 0 less than theta P less than 2 pi. And we consider the map P goes to x theta P as an element in the conjugacy class. So the space conjugacy class is X. So this is a conjugacy class in X parametrized by this. So the question then becomes, what is the Haar measure of SU2? And what are the irreducible characters? And how is this uniformly distributed in this setting? So in the context that the elliptic curve, if E has no complex multiplication, we look at the L functions. By the way, I think you all know that in case of a compact group, the irreducible representations are countable. Therefore, I'm going to use this index notation. Hmm.
One is in the center.
You mean this one? Should be pi? Yeah. I think because it's duplicated, right? It's symmetric. So between minus pi and pi, or between? Yeah, maybe minus pi to pi. For symmetry reasons? Is that what you want? Like that? Maybe this way. Yes, you're probably right. Is that better? We could. It wouldn't matter, right?
Thinking of this conjugacy classes will be parameterized by some sort of longitude on the tree, and it will only go from minus pi by.
Yeah, but there is, as he says, symmetry between x theta and x minus theta, of flipping, right? But anyway,
That tree here.
You could start at 0 and 2 pi and whatever, but as long as the interval just got 2 pi in it, I think. You're right that I could have used one or the other. It's same thing like here. It's cos of theta p could be cos of minus theta p too. So I could have used it the other way too. There is the symmetry, which we will not worry about, yeah? But I'll just map it to this conjugacy class. And then the question is, as I vary the conjugacy, as I vary the primes, is it uniformly distributed? And that requires me to go checking each irreducible representation and constructing this L function. And I can write this L function down very concretely. Let's do that. Let's do that right now. See, you have the standard representation of SU2, standard two-dimensional representation of SU2, namely take the matrix to itself, right? That's called a standard representation. And then we have the symmetric powers of the standard representation. So if you have rho standard, which basically takes the matrix X, matrix G and to G, so SU2 looks like this is a standard representation. Well, all the irreducible representations of SU2 are given by the mth symmetric power of the standard representation. And you can work out what that would mean in this context. Then LS rho sub m turns out to be equal to the product over the primes P, product over J going from, this is where I'm going to probably mess up, minus m to m, perhaps. Let's see, 1 minus e to the I theta p j over p to the s inverse. And I think one can write it down in this horrible way. And then the question then becomes, does this extend analytically to real s bigger than or equal to 1? And can I prove it doesn't vanish there so that I can establish that it's uniformly distributed? And the image of the Haar measure in X is this calculation 2 over pi sine squared theta d theta. It's a nice calculation. It's done in this broker Tom Deek book, as far as I know. That's about the only book I saw it in. So you can check that out. And this is all for curves without complex multiplication. If the curve has complex multiplication, then the interval to use is not, the group to use is not that, but the group to use is more or less something like this, a torus. And then the L series that come correspond to Hecke L series. And those Hecke L series had already been analyzed by Hecke. That's why I go back to Hecke. And then so it was already known. So in the 1960s, I think, when Sato and Tate made this conjecture, they made the comment if the elliptic curve had complex multiplication, more or less Hecke's work shows that they're uniformly distributed. But in the non-CM case, they really didn't know how to do it. Sayre reformalized it in this fashion. And then the question is, what are these L functions? And do they come from automorphic theory? In all L functions, in some sense, should. So this is in the case that rho is the standard representation, LS rho standard, essentially, I say essentially because there's some shift which we don't need to worry about, is the L function of the elliptic curve. Now you may know about the L function of the elliptic curve. This is defined as product P 1 minus a sub p over p to the s plus 1 over p to the 2s minus 1. Looks very much like this Ramanujan example that was given in the morning, and it's very close to that. This cell function comes from a modular form is the famous Taniyama modularity conjecture. Taniyama conjecture that Wiles had to prove before he proved Fermat's theorem, right? So this is Taniyama conjecture, Wiles' theorem. So the automorphy, that this is an automorphic L function, is the special case. It requires this. Now, in other words, if we want to get our hands on this conjecture, you have to show all of these L functions are automorphic. And if you had that all of these L functions are automorphic, then remember that famous theorem of Jacquet and Shalaika that said any automorphic L function doesn't vanish on the line real S equals 1. At the end of their paper, they said, well, I don't know what good this thing is going to be, but this is what all the prime number theorems have been doing. They've been showing non-vanishing on the line real S equals 1, which seem to be very important. So we're at a stage where, as I said, we have many proofs looking for a theorem. And so all these L functions, we know coming from automorphic side are non-vanishing, they're analytic, non-vanishing. Therefore, there has to be some theorem telling you about uniform distribution. And this is the case in point. So now, can we actually show that these are all automorphic L functions? So the Taniyama conjecture is only the standard representation is automorphic. That's proved. But all these other powers, symmetric powers, are all the automorphic. And now, as of 2024, we know that they are. But I'm going to talk about a little earlier work, 2013 maybe, which goes back before we didn't know that. We knew what is called potential automorphy. And potential automorphy turned out to be enough to prove this. So that's what I want to talk about. Right. Now, as with any program, many tools get developed, and exactly how to put these tools together requires knowledge and ingenuity. So there are quite a number of tools that we need to focus our attention on. So let me try to summarize these tools. So let me just say, due to the work of a lot of people, this is being televised. We better get these straight. Anyway, due to many people. So firstly, the modularity conjecture in general. Of course, Wiles before. The modularity conjecture. The Taniyama modularity conjecture. Taylor proved potential automorphy. I'll explain this word in a second, of the symmetric mth power of the standard. 33. This was 2008. And then recently, quite a number of people, I'm not going to get this right because I don't think I put this in here. At the time I wrote it, it didn't have it there. But certainly, here. So maybe the name's Clozel, Harris, Shepard Barron. Taylor. So all these people now have established automorphy. Oh. So in other words, what does this mean? It means that this L function here is that Langlands L function, LS pi for some pi. And remember, Langlands showed that all these L functions extend analytically to the entire complex plane. And Jacka and Shalaika showed that they don't vanish on the line one. Therefore, you can apply the Sayre formalism and deduce the equidistribution theorem. So that's the method. But it's interesting to know that this is recent. This is very recent. So like in the last 5 years, it's very interesting to see how without full automorphy, but only potential automorphy, Euler was able to prove the Sato-Tate conjecture. The reason is the Sayre formalism doesn't ask you to show automorphy at all. It just asks you to show that it has analytic continuation to the line real S equals 1 and doesn't vanish there. So you really don't need automorphy as such. And so let me now try to give you some sort of crash course. So I hope people are not sleeping and you will be able to understand something. Don't worry about whether you understand all the words or not, but I'm sure you will understand the general philosophy behind all these things. All right. Now, in our setup this morning, we talked about K is an algebraic number field. And we talked about the Adel ring. And we talked about somehow representations of the Adel ring. And we took an automorphic representation, which was one of those representations of that thing. And to that, we associated an L function via Langlands. I didn't tell you exactly how, but I told you that he did it. And so this is the general setup. So this has kind of a picture where you have a field K and you have some object pi associated to representation of the Adel ring. Now, given an algebraic number field, I can consider an extension field. Yeah? And so the question is there a natural object that I can associate it's called base change. So take an F pi downstairs. Can I view some sort of base change map upstairs? Conversely, if I had an automorphic representation here, can I restrict myself and get some sort of pi downstairs? So in other words, there's something called the automorphic induction map, which will give rise to a representation of GLN AK. So the idea of somehow functoriality, this is a functoriality principle. And it's very natural, lifting an object downstairs to an object upstairs. and restricting an object upstairs to something downstairs. And the work of Arthur and Clauzel shows that these exist for all nilpotent extensions. So these are still conjectural that they exist, but in the case that f over k is Galois and nilpotent, these exist. So Arthur-Clauzel theory, they have a Arthur-Clauzel theory. If f over k is Galois and nilpotent, that means the Galois group is nilpotent, then the base change maps and the automorphic induction maps exist. Okay, that was a big theorem. So step ingredient number 1. And ingredient number 2 is, I mentioned the Jacquet-Shalaika theorem this morning. Ingredient number 2 as I said, don't worry if you don't understand the technical language, but you will be able to understand how these are put together. If you just bear with it for a second. 2, the Jacquet-Shalaika theorem. L1 plus IT pi is not 0 for any automorphic representation for any pi of GL and AK. So we just leave it at that. And the third ingredient, okay, this is a little tricky. It has to do with tensor products of representations. So it's again this functoriality idea. See, in representation theory, you can take tensor products. So if pi1 is an automorphic representation, pi2 is automorphic representation, you can certainly take tensor product. And then the question is, can I construct an L function attached to that? From a standpoint of an Euler product, it's very easy. You just take all the products of the eigenvalues and concoct a series. The question is that an automorphic L function? Now that's a big conjecture, open still, in the Langlands program. That when you take two automorphic representations and they take their tensor product, it is still automorphic. And the answer is conjectured to be yes. However, there's a famous theorem, it's all called Rankin-Selberg theory. Due to Shalaika and Shahidi. Okay, Jacquet should probably be in here as well. Jacquet, Shalaika, and Shahidi. Basically, that says if pi1, pi2 are automorphic, then LS pi1 tensor pi2 is analytic and non-vanishing on real S equals 1. So here, the assertion is not being made that it's automorphic, but only that it's analytic and non-vanishing, which is probably all that we need in our punchline. So we have this third ingredient, and now, now what we have is we have probably most of the setup. In the course of time, the issue of establishing whether a particular L function is automorphic got changed to establishing whether a particular L function is potentially automorphic. So you're trying to prove that the L function you constructed comes from an automorphic representation of the field K. But the idea is, supposing I go to a larger extension and I show that it's automorphic there, then it's called potentially automorphic. So we say pi is potentially automorphic if base change of pi, I should have put a subscript there, base change of pi to some larger field is automorphic. So now you see we don't need that full strength of automorphy. Again, we're weakening the thing by moving to a larger field, and maybe we can get away with it for the purpose of equidistribution theorem. And that's how it is done. So what Taylor proves, so Taylor's theorem outline, so Taylor's theorem that I'm talking about is this 2008 theorem. And from this paper follows the Sato-Tate conjecture, which is the equidistribution with respect to this measure of those angles. So it'll come out because we will show that these L functions are potentially automorphic, and then we'll squeeze out the theorem appropriately. So step one, if M is odd, then symmetric mth power of rho standard is automorphic over F for any K contained in F, contained in L, with L over F solvable. So here, what are we saying? We're starting, we have this base field K. We could have taken K to be Q, by the way, but let's stick with the general notation. Start with the base field K. We have the M symmetric power, which we're trying to show is automorphic here, but we don't know how to do that. We are saying that you can base change it to L and have it automorphic there, and then it's automorphic as long as over any field F, such as long as this extension is nilpotent. And you can see where that word nilpotent, solvable comes, because we're obviously going to use solvability means you can stratify the group into cyclic extensions, and in each cyclic extension you can apply this Arthur Clausel principle. And so that's exactly how they do it. In other words, i.e., we're trying to prove the symmetric power of the standard representation is automorphic, but we're proving that this restricted to F is automorphic for all F with L over F solvable. So that's step number one. And step number two is essentially Brouwer induction theorem applied in this context. So I mentioned the Brouwer induction theorem in the morning. That says that basically any representation can be written as integer linear combination of inductions of one-dimensional representations coming from various nilpotent subgroups. Step two. So let G be the Galois group. Write 1 a trivial thing is induction from H to G, Hi to G of psi I, where the AIs are integers and psi I's are one-dimensional characters and HIs are certain nilpotent subgroups. So having written that, you are interested in LS symmetric power. This is what we want to get our hands on, this L function. But tensor it with 1, which is the same. Okay. And now use 1 is the sum of the AI induction. Therefore, this now becomes a product over the I's, L of S, symmetric M, rho standard. I'll just write rho for now on. Okay. Tensor induction Hi to G of psi I to the power AI. So this is this is an interesting trick, isn't it? This is what you want to get your hands on. You tensor it with 1, which is the same thing, and then write your 1 as a linear combination of these things. And then because of the properties of L functions, you can write this as a product, and then you get this. Good. Now, the interesting thing is the Artin reciprocity law tells you that if I have a one-dimensional character, it's automorphic. That's another way of saying it. So this is really what, so we can go back. So this apply two things. L S symmetric M, rho, restricted to the subfield fixed by. So here I'm applying what's called the Frobenius reciprocity. So Frobenius symmetric M, rho, tensor induction H I to G of psi I is the induction from Hi to G of the symmetric mth power of rho restricted to the fixed field of Hi tensor psi I. So I'm going to apply this Frobenius reciprocity theorem to this piece here, and then use the fact that, so the L function of this guy, this representation, is the same as the L function of this guy. And then there's a little exercise you have to do. The L functions are invariant under the induction operator. Therefore, I can drop the induction thing and just write this. This is basic functorial property. So once I have this, what is this? Well, HIs are nilpotent. And therefore, the subfield fixed by HI is one of these guys again in this step 1. And therefore, it is solvable. Therefore, the symmetric power representation is automorphic over any such field. So I can go back and say, this guy is automorphic over LHI. This is automorphic over LHI because it's a character. And therefore, this is automorphic over that field. And therefore, what do we have? We have an automorphic L function here. And therefore, the mth symmetric power now is analytic for real S bigger than or equal to 1. And it's non-vanishing there because I've recognized this as an automorphic L function thanks to Jacques et Shalaika that tell me as long as it's automorphic, it doesn't vanish. Therefore, for the odd numbers, M, we've managed to show step 0, the part of Sayre's formalism. You need to get analytic continuation and non-vanishing. We got it for all the odd powers. So we need to now do for the even powers, and that's what's remaining. And for that, we use a high school algebra trick. So what is the high school algebra trick? The high school algebra trick is a trigonometric identity Oh, I'm running out of time. So the high school algebra trick is exercise sine m theta over sine theta plus sine m plus 2 theta over sine theta equals sine m plus 1 theta over sine theta times sine 2 theta over sine theta. Now I know sine 2 theta, and all of you know, is 2 sine theta cos theta. I should write cos theta here, but I'd rather write it like that. Simple reason is because the character of the m symmetric power is sine m plus 1 theta over sine theta. Okay, so I can take this high school trigonometric exercise and change it to say this implies that the L symmetric power standard times the L symmetric power of m plus 1 rho standard is equal to the L symmetric power of rho tensor L, sorry, let's tensor the symmetric one. So let's just drop this rho standard. So I finished showing whatever I wanted to show when m is odd. But for m even, I'm going to run an induction argument. So if m is even, so when m is even, let's not worry about the base case. So and m is even. So I've got even numbers here. Supposing I've proved my result here, then m is even. So m in this, sorry, m minus 1 is even. What am I trying to say? I'm trying to say m minus 1 is even. So m is odd. So this case, m is odd, right? So we now assume m minus 1 even, and of course m plus 1 is even. And I'm going to try and do an induction. And in that case, m is odd. And by what Taylor just established, the m symmetric power is potentially automorphic. So we have the property that we need. If it's potentially automorphic, it's automorphic at some larger extension. And so the Rankin-Selberg theory kicks in and then says the Rankin-Selberg product of two automorphic things, we're not saying it's automorphic, that's still an open problem, but we know it's analytic and non-vanishing. So this part here comes from the Shahidi Jacques Shalika paper. So this is analytic and non-vanishing for real S equals 1. And therefore, by induction, I've got this guy, analytic, so I divide out and I get the next guy. So this is this clever, very clever argument of Taylor in 2008 without doing automorphy. Now we know it's automorphic, this recent result, but you don't need the full strength of the Langlands program in order to do this. So I hope this is an illustration of some of the heavy duty theory that was discussed in the morning, very abstract Langlands program, that it has concrete applications to equidistribution results in very down-to-earth terms. Okay, so that's all I have to say. I lectured from this paper called Sato-Tate conjecture and generalizations, which was published joint paper with my brother Kumar. Current Trends in Science, published by the Indian National Science Academy. So it's available on my homepage if you want it and to study from it. Yeah.
We are taking elliptic process. Instead of that, if I take a modular form, I take the Sato-Tate parameters and divide the say k by 2 or k minus, and still I'll be fine. The same thing.
Absolutely. That's exactly it. So remember that the base case was automorphy, the Taniyama conjecture, but you're starting from a modular form. You already have automorphy, okay? And then you're now building these higher symmetric powers. So all this machinery works mutatis mutandis, and everything goes through, and you're absolutely right. So you just have to distinguish modular forms of CM type versus modular forms of non-CM type. And as long as it's a modular form of non-CM type, all of this will work. And of course, the CM type is already again back to Hecke. Yeah. So for the tau function, yes, for the tau function, as he correctly points out, it's a very, 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 it's actually very nice that you say that, because my guess about Ramanujan is that he was always down to earth, and to explain Sato-Tate, I had to explain to you elliptic curves. But to explain the tau function, you don't need that. You just need that power series expansion, right? So what he's saying is absolutely correct. If you take the Ramanujan tau function and you divide out by 2p to the 11 halves, this is a number that lies between -1 and 1. And the question is, are these numbers equidistributed? And the answer is yes, the same thing goes through. Because there's nothing about elliptic curves that these guys used. All they did was they did an automorphy at row 1, the first level. So same thing goes through. Yes, good point. Yeah. Yeah.
The issue to is because of like the GL2 object, and then you take the real.
Yeah. 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 There's a theoretical explanation for that. Yeah, you're right. It's for the Lia.
For other groups, can you tell?
That's a good question. So what do you mean? You mean that, for example, for other varieties, abelian varieties, or something like that, or for curves, or what?
So if I take
Mm-hmm.
so I take the dual group.
Yeah.
Then I do the same thing.
Well, what do you mean to do the same thing? So the point is that as long as you have a compact group and the set of all irreducible representations is a countable set, and so you have to check the Weil criterion, the generalized Weil, for each of those things. As long as you have a map from one set, your set that you're interested in, into the space of conjugacy classes, you can do the same thing. So the mechanism works. Yes.
Okay, so if you start with something automorphic, you are going to get the result. Like
If the collection of items that you have are parametrized by an automorphic representation, yes, you'll get the result. But if your things are not, then this is not going to work. Yeah, it's like trying to use a screwdriver to hammer a nail. Yeah.
any other question? Not then. What is the meaning of phase change when you?
Is this my water?
Yes.
Oh, I really need it. Is it for me? Really?
Yeah.
Sure. Okay. Yeah, I really need it now. Yeah. What is the meaning of what?
Phase change is phase change. How do you
Yeah. Yeah. So base change. So if I have, what happened to the eraser? It's over there. I mean, base change is easy to describe in terms of L series.
Yeah,
Yeah, it's a conjecture. Yeah. Yeah. So yeah. Well, that's what this the Arthur Selberg theory is all about. So if I have an automorphic representation of GLN AK, say, okay, and if I have a field extension, so I have this pi downstairs, and I want to kind of build it up to some base change of pi. Of course, there's a f over k business, so I should perhaps put base change f over k of pi, but too much notation. Let's just drop some of that stuff. The L function that you started out with will have some sort of Sato-Tate parameters, what are called, these lambda pi's. So there's a double product actually here. Also, I should not be using p. I should be using the prime ideals. But let's not worry about that. Let's just keep things simple for a moment. Then what happens if this is a Galois extension? Then what you would do is you would take all the Artin L functions attached to the Galois representations, and corresponding to that, you get a certain Euler product with certain eigenvalues. And what you would then do, the base change would be twisting all these lambda pi's with all those eigenvalues, all of them, all the representations that appear in everything. So, and then you would get a new object of which formally this would sit as a divisor of that infinite product. And the question is, it seems easier to prove this larger product is an automorphic representation than it is sometimes to prove this is. And what this shows is that some potential automorphy is sufficient for many of these classical questions. And you're right that so when we get some very, very concrete questions, the ability to translate that question into automorphic language, if it means anything, is an important first step. Sometimes the problems have no such interpretation. Uniform distribution of square root 2n cubed, or square root 2n, let's say, is a fractional part of this guy, uniformly distributed mod 1. You would not use L functions for that. Okay, when do you use something and when you don't use? Again, the screwdriver and hammer business. You have to figure out when to use something and what to use it for. So these questions, L functions are useful, but these other questions that seem to work for the equidistribution, and I'm suspecting there are a lot of uniform distribution questions for, eigenvalues of Frobenius for curves, and Kiran Kedlaya and other people have been thinking about Sato-Tate question for curves. So might be, if you're interested in that, you might be worth looking into those papers. They're accessible, and Kiran doesn't write in, he writes in understandable language. So I think you should be able to follow that, and that would fit into this L function scheme.